My name is Danesh Venugopalan. I'm one of the faculty members of Brilliant Group of Institutions taking classes from 10th to 12th teaching chemistry and biology. Today I would like to talk about a topic named hybridization. This is one of the most important topics that comes in one of the chapters in class 11th chemistry. In hybridization, we can see that there is an intermixing of atomic orbitals happening. So, whenever you hear a particular name about a phenomenon, you should think why such phenomena happen in nature. One of the most accepted theory about chemical bonding is the concept of hybridization. The conventional definition of hybridization is intermixing of atomic orbitals to form a new whole set of orbitals called as the hybrid orbitals. Now, why would an atom do that? Why can't the atoms combine by simply mixing their atomic orbitals? Or why can't they overlap their atomic orbitals to form a chemical bond? Before we go into the details of that, let me just tell you that there are so many atomic orbitals which are available in an atom, and as you are well aware that these atomic orbitals are the regions around the nucleus of an atom where there is maximum probability of finding electrons. So whenever an atom is going to form a chemical bond, it is seen that the central atom just intermixes their atomic orbitals available to create a new set of orbitals called hybrid orbitals, and these hybrid orbitals are the one which takes part in bonding. Now one should ask, why can't the atom just leave their atomic orbitals as such and then overlap it with the other atomic orbitals of the atom and create a bond? The answer lies with the most basic concept in bonding, which is every atom or every element in nature is in the course of finding stability. As you all know that few atoms are stable, but many of the atoms are unstable. And these unstable atoms generally get stabilized by forming bonds with other elements. So during this bond formation, one should see the most significant change that is happening. And I would say it's nothing but lowering of energy. We can generalize to some extent that most of the chemical bond formations are happening because by forming these kind of chemical bonds, an atom or an element can lower its energy. So ultimately all chemical bonds are formed to lower the energy of the systems or lower the energy of the elements, because always a lower energy state makes stable structures. And here, in the concept of hybridization, we see that there is intermixing of atomic orbitals. So we have different atomic orbitals in an atom. Coming to the concepts of orbitals, you know that the shape of an s orbital is spherical. The shape of p orbitals, it can be of three types. We have the px, the py, and the pz. All these three orbitals belongs to the p subshell, and all of them are differentiated based on the orientation that they take in the coordinate axis. Let's say for example the px orbitals lies along the x-axis, the py orbital lies along the y-axis, the pz orbital lies along the z-axis. Now during the intermixing of these atomic orbitals, what you see there is these atomic orbitals, which are having relatively different energies, they intermix together to form a whole new set of orbitals called hybrid orbitals. Now let's look at one example where this kind of hybrid orbital formation takes place. The best example to demonstrate that is the formation of a molecule called as methane. You know that methane is a molecule where carbon is the central atom, and carbon forms 4 different covalent bonds with hydrogen. So all these covalent bonds formed by carbon with hydrogen are formed in such a way that the carbon atoms forms their atomic orbitals or turns their atomic orbitals into hybrid orbitals. And we call such hybrid orbitals of carbon as the sp3 hybrid orbital. So what happens during the bond formation, or what happens during the formation of methane molecule? Let's look at that in a way by which we can explain the formation of methane molecule by using the theory of hybridization. So if you consider a carbon atom whose atomic number is 6, and we know that the electronic configuration of this carbon atom is 1s2, 2s2 and 2p2. This is the electronic configuration of a ground state carbon atom. That means a carbon atom which is having all its electrons present in its default atomic orbitals. So if you look at the orbital diagram, we can say there are 2 electrons in the 1s orbital, there are 2 electrons in the 2s orbital, there are 2 electrons in the 2p orbital. But it is seen that prior to hybridization, prior to intermixing of atomic orbitals, carbon atom is going to excite one of its 2s electron into an empty 2p orbital. So what you just saw is during bond formation, prior to hybridization or after the hybridization, either way, the carbon atoms are going to excite their 2s electron into an empty 2p orbital. Now we can see that there are 1, 2, 3, 4 unpaired electrons present, and that is what is the prerequisite for the formation of methane molecule, because in methane molecule you have one carbon atom sharing 4 of its electrons with each of the hydrogen atom. So you have total 4 hydrogen, so there is a requirement of 4 electrons there. Now after this excitation is over, we see there is an intermixing of these orbitals, where one of the 2s orbital gets mixed with 3 of the 2p orbitals. Since we have a px orbital involved, a py orbital involved and a pz orbital involved, and also the 2s orbital, they all will mix up together to form a whole new set of orbitals. And the way how it mixes is, we have one s orbital involved, and then we have 3 p orbitals involved. So a total of 4 orbitals are mixed here. A total of 4 atomic orbitals are present here. These 4 atomic orbitals, when they overlap, they generate an entirely new set of 4 hybrid orbitals. And you can look at the structure of these 4 hybrid orbitals. Say for example, if we look at the sp3 hybridization, we can say over here you can see that these are the different atomic orbitals. We have the s orbital, which is spherically symmetrical. We have the px orbital, which is lying along the x-axis. We have the py orbital, which is lying along the y-axis. We have pz orbital, which is lying along the z-axis. Now all these 4 atomic orbitals are going to overlap. As you can see here, they are overlapping, results in a mixed kind of situation where you have these atomic orbitals mixing together to generate entirely new set of orbitals. Now why would an atom do that? What is the reason behind this overlapping? Well, we can say the real reason behind this overlapping is to generate the new set of orbitals which are having relatively lower energy than the original atomic orbitals. I repeat, hybrid orbitals are having relatively lower energy than the original atomic orbitals. So you can see that there is generation of new set of orbitals, and those new set of orbitals can be visualized here. So you see the intermixing there, and you have witnessed the formation of 4 new set of orbitals. And as you can see in this diagram, all the 4 hybrid orbitals are of having same shape and similar energy. And the way how these hybrid orbitals are arranged in space can be predicted based on the same logic that we have been using in VSEPR theory. Because we know that in VSEPR theory, electron pairs around the central atom will be located or will be distributed in such a way that they will have the least repulsion between them. The same logic is applied here for hybrid orbitals as well. For example, if I have two hybrid orbitals, they will be staying in a linear shape because that is the least possible repulsive state in which those two orbitals can exist. If there are three orbitals present, the best way how they can exist is, as you can see here, if I show you the kind of possible arrangements of these hybrid orbitals. If I have two orbitals present, they will be arranged in linear geometry. If I have three of them, they will be arranged in a trigonal planar geometry. And if I have four of them, this gives you a new kind of geometry which is called as tetrahedral geometry. As you can see that you can make out a tetrahedron out of this. There are four orbitals, one lying above, one lying below, and two of them are in and out of the planes. So a total of four orbitals are here. Now, if you think about the carbon atom, which is having these four orbitals, imagine the carbon is the central atom, and the carbon atom has got one hybrid orbital here, one hybrid orbital here, one hybrid orbital here, and one hybrid orbital here. This is how you represent a tetrahedral geometry. And all these hybrid orbitals are now having single electrons, and that will be very clear to you from this orbital diagram. As you can see that each of these atomic orbitals were having single electrons before hybridization. Even after hybridization, those electrons remains there, and we can call these individual hybrid orbitals as the sp3 hybrid orbitals. So there are a total of 4 sp3 hybrid orbitals, and each of them have one electron. Now, these hybrid orbitals are going to form a bond with hydrogen. As you know that hydrogen has only one electron and it is localized in the s orbital of hydrogen. Now, during the chemical bond formation, each hydrogen atom will come and overlap their s orbitals with the hybrid orbitals of carbon. As you can see here, this kind of overlapping which happens between the s orbital and the hybrid orbital of carbon is a kind of overlapping that happens from end to end. This kind of overlapping results in a chemical bond in nature called as the sigma bond. So always remember that whenever there is involvement of hybrid orbitals, whenever there is hybridization, the kind of bond formed will be always sigma bond. Remember, a hybrid orbital is never able to form a kind of bond which we call as the pi bond. Pi bonds are generally created by lateral overlapping. So over here, it is a sigma bond formed, and this sigma bond is formed by axial overlapping. Hope that concept is very clear to you. As I said, the geometry of this molecule is tetrahedral, and the bond angle refers to the angle between the two hybrid orbitals, any two hybrid orbitals. So over here, the bond angle in a tetrahedral geometry will be always 109.5, and that defines how a methane molecule is formed by hybridization. So let me just summarize these points and make a clear picture to you. As I said in the beginning, every molecule, every element is towards is in a race of achieving a lower energy state. For that, they find different options. One of the options that an atom or an element in a molecule can do or can achieve stability is by forming hybrid orbitals. Now, why are hybrid orbitals formed? Hybrid orbitals are of having very low energy compared to the original atomic orbitals. And please make sure that whenever you study hybridization, you should remember these points, like why hybridization happens, what is the cause of hybridization, and during hybridization, one should understand that the atomic orbitals that participate in hybridization, let's say I have 4 of them participating in hybridization, then I'll have 4 hybrid orbitals. If I have 3 of them participating, then I'll have 3 hybrid orbitals. So always the number of atomic orbitals that takes part in hybridization is equal to the number of hybrid orbitals formed. So I hope you are clear with the hybridization of methane molecule, and please remember this important concept. And here in Brilliant, we are mainly focusing on this kind of conceptual explanations or a video-based explanation for the concepts to be made clear, because one does not have to imagine what is happening inside the molecular level. Once, if we are able to depict it in the form of a kind of video, then it will be very easy for you to understand. I hope these things are clear for you. Thank you so much.